Let's try to investigate maxima and minima of functions in several variables, and in particular for our interest a function of two variables. So we begin our journey by recalling the extreme value property of continuous functions in one variable. So let us recall what we have seen in calculus 1. So if D is a closed and bounded subset of R and f is a continuous real valued function on D, then you have seen that f has a maximum and also a minimum that occurs in the set D. So if f is a real valued function which is continuous on a closed and bounded subset of R, then it has a maximum and a minimum in the subset D. So what it means is the following. So there exists a point A in D such that f of a is less than or equal to f of x for all x in D. This corresponds to the minimum, and there must exist a B in D such that f of b is bigger than or equal to f of x for all x in D. So in this case, A is a point where minimum occurs and B is a point where maximum occurs for the function f in D. Note that the important part is that A and B, these two elements, must lie in the set D, that is the domain of the function. So you may have also seen this in calculus 1 that if you remove the conditions of the subset D to be closed and bounded, then our assertion is not anymore true. So what are counter examples? So suppose I want to look at a counter example where the subset D is not closed. So for example, you could take D to be the open interval AB, and you could take f to be x. So f of x is equal to x, f is the identity function. Then you can see that even though the supremum and infimum of the function exists in the open interval, but they are not attained by any value or any point in the open interval. So even the supremum and infimum of f exist, the maximum or the minimum of the function does not exist in D. What happens if the set is not bounded? You could take D to be the whole of R, and again the identity function works. In that case, forget about having a maximum or minimum. You could easily see that f is an unbounded function. So what we are going to do now is that we are going to look at a higher dimensional analog, and strictly speaking a two-dimensional analog of this theorem that I have just mentioned. So first, a definition. So suppose that D is a subset of R2. We say that D is a bounded set if there exists alpha which is bigger than 0, such that norm of all the elements in D is bounded above by the quantity alpha. So then what is the extreme value property in this case? So suppose that we have a non-empty subset of R2, and suppose that D is closed and bounded. So just like in the case of one variable calculus, so we have a subset D which are closed and bounded, and f is a continuous function on D. So f is a continuous real valued function on D. So then our first claim is that f is bounded, and not only that, f attains its bounds. So there must exist 2 points x1 y1 and x2 y2 in D, such that f of x1 y1 is the minimum of all the values that f takes in the subset D, and f of x2 y2 is the maximum of the set of all values that f takes in the subset D. So note that we have mentioned that these 2 points where maximum and minimum are going to occur are points in D itself. So the proof of this theorem is quite complicated, and we are going to omit the proof and we will go forward. So let us introduce you to some definitions which are analogous to the functions in one variable. So again, suppose that D is a subset of R2 and f is a real valued function on D, and suppose I take a point AB in D. Now we say that f has a local maxima at the point AB if f of AB is bigger than or equal to f of xy for all xy in a neighborhood of this point, of the point AB. So let me read through this. The function f is said to have a local maxima at AB if there exists r bigger than 0. So if there exists r bigger than 0 such that f of AB is bigger than or equal to f of xy for all xy in the neighborhood of AB of radius r, and we also want these points to belong to D just to make sure everything is good. So similarly, one could define local minima of a function at a point AB. So f is said to have a local minima at the point AB if there exists again r bigger than 0 such that f of AB, here just the sign changes, is less than or equal to f of xy for all xy in a neighborhood of AB that is contained inside D. So these are local maxima and local minima that we are going to concentrate on. So there are two definitions that you may have seen in your one variable calculus. They are called global maxima and global minima. So what is a global maxima? So f is said to have a global maxima at the point AB if the following happens. So f of AB is bigger than or equal to f of xy for all xy in the set D, and it is said to have a global minima at AB if f of AB is less than or equal to f of xy. So we are not going to talk much about global maxima and global minima. So we are only going to concentrate on local maxima and local minima of a function. So you have seen in your calculus 1 that if D is a subset of R, if D is a subset of R and f is a real valued function on D, so if f has a local maxima or a local minima at the point C, then the derivative of f at the point C must be equal to 0. So here is a two-dimensional analog. So suppose that D is a subset of R2, f is a real valued function on D, and AB is a point in D. So the result says that if f has a local maxima or a local minima at the point AB, and if both the first order partial derivatives exist at the point AB, then both the partial derivatives, both the first order partial derivatives vanish at the point AB. In particular, what it says is the following, that if the gradient of f at the point AB exists, so if it exists, then it is equal to 0. So gradient of f at AB is equal to 0, 0. So how do we prove it? If we know this result from one variable calculus, then the proof is really simple. So what we do is a very standard trick. So suppose that f has a local minima or a local maxima at the point AB. So we are going to look at what happens in the x direction and in the y direction separately, and this will give us the proof. So what we are going to do is that we are defining a function gx, and this gx is defined as f of x comma b. So we are going to fix y at the point B and we are going to vary x. So in other words, what we are going to do is that we are going to take the graph of the function and we are going to intersect the graph of the function with the plane y equal to b. Now this function gx that we are having here is a single variable function, and if f has a local minima or a local maxima, then g must also have a local maxima or a local minima. So local maxima or a local minima at the point x equal to a, and And what do we have in that case? If g prime x exists, then g prime a must be equal to 0. So this is actually the proof. So let me write it down. So if fxab exists, so then g prime a exists, because what is fxab? So what is fxab? So this is just g prime at the point a. So if fxab exists, then this exists, and then by one variable calculus we know that this is equal to 0, and consequently we have proved that in such a case fxab is equal to 0 as well. Similarly, you could define a function, say h of y, which is given by f of a comma y, and you could go through the same argument to produce that if y ab must be equal to 0. Now, just like in the case of single variable calculus, we will see that if gradient of f is equal to 0 at a point, it does not mean that that the function will have a local maxima or a local minima, but we will come to this in a moment. So first we have got a set of points with certain properties that if the gradient of f exists at those points, then they must be equal to 0 0, or the gradient must be equal to the 0 vector. So we should give them a name, give this kind of points a name. So a point AB in D is said to be a critical point if either gradient of f at the point AB does not exist, so one of the partial derivatives do not exist, and or at least one of the partial derivatives do not exist, or what do we have is that the gradient is the 0 vector. So remember, either one of the partial derivatives do not exist or the gradient is the 0 vector. So such points are called critical points. And what we have derived in our previous slide is the following. So if f has a local maxima or a local minima at the point C in D, so I have written it in a vector form, then C must be a critical point. However, as I have just mentioned, that the converse is not true. I'll give you a counter example to this fact in a moment. So first let me go through a very simple example. I'll call it a very pleasant one, why you will understand by the end of this video. So suppose I consider this function on so f is a function from R2 to R. So I have taken D to be the set of all real tuples. So fxy is given by x square plus y square minus 2x minus 6y plus 14. So to determine what are the critical points, I have to compute what are the partial derivatives of f with respect to x and y. So it easily turns out that fx at a point xy is given by 2x minus 2, so 2x minus 2, and similarly fy at the point xy is given by 2y minus 6. So if we solve fxxy equal to 0 and if yxy equal to 0, we are going to see that the only critical point is given by 1, 3. So note that it could so happen that there could exist a critical point where at least one of the partial derivatives cease to exist. But in this case, this is a very nice example where these partial derivatives exist at all the points. So we do not bother about the case where the partial derivatives may not exist. So let me write down if around the point 1, 3. So do not really bother about this term around. You will know the meaning if you have seen Taylor's theorem in calculus 1, but otherwise just follow what I am trying to do here. So a simple expression of f of xy can be written as follows. It is x minus 1 whole square plus y minus 3 whole square plus 4, and you can see that f of 1, 3, if I just put x equal to 1, y equal to 3, then this becomes equal to 0, this becomes equal to 0, and f of 1, 3 is equal to 4. But if you look at this whole expression, you can see that this whole part, x minus 1 whole square plus y minus 3 whole square, this is always bigger than or equal to 0. And as a consequence, f of xy is bigger than or equal to 4 for all xy in R2. So what we have shown is the following, that f of xy is bigger than or equal to f of 1 comma 3 for all xy in R2. As such, what we have proved is that f has a global minima at the point 1 comma 3. Here is a rather concerning example which will serve as a example which illustrates that critical points do not guarantee that the function that we are considering has either a local maxima or a local minima. So here is the example. So I take f of xy to be equal to x square minus y square. Again, our domain is whole of R2. So if we want to differentiate this function with respect to x, namely we want to compute the partial derivative with respect to x and y, we will see that fx is equal to 2x and fy is equal to minus 2y, and consequently the critical point, the only critical point, is given by the origin. Now let us see what happens if we look at the x direction at the point 0, 0. So here what we have is we are just trying to mimic what we have, the logic that we have used in the proof of the relevant proposition, let's say. So suppose that gx is equal to f of x comma 0, which is of course given by x square. What is g prime x? G prime x is 2x. So at the point x equal to 0, so we see that g prime of 0 is equal to 0. And what happens if we differentiate this function once more? So g double prime x, the double derivative of g with respect to x, is equal to 2, and of course this is true for all x, and g prime of 0 is also equal to 2, which is bigger than 0. So by the second derivative test for the one variable calculus, what we can see is that on the line y equal to 0 or in the direction of x, g has a minima. G has a local minima at the point x equal to 0. So in terms of multivariable calculus, if we consider the line y equal to 0, which is the x-axis, so then f of xy has a local minima on the line y equal to 0. So we do not know what happens outside the x-axis, but on the x-axis it has a local minima. Now let us try to understand what happens in the direction of y. So again, I define h of y to be equal to f of 0y, and this function turns out to be equal to minus of y square. So what is h prime y? It is minus 2y. We can see that h prime of 0 is equal to 0. So of course this is bound to happen because we know that fy at 0, 0 is equal to 0. So what is h double prime y? The double derivative of h with respect to y, this is minus 2, and this is constant. So that means that h double prime at the point 0 is always going to be minus 2, which is less than 0. But again, from one variable calculus or the second derivative test for one variable calculus, we can assert that h has a maxima at the point y equal to 0 on the line x equal to 0, that is the y-axis. So here what we have seen is that fx has a local minima on the line y equal to 0, and here we have seen that f of xy has a local minima, or has a local maxima in fact, on the line x equal to 0, which is the y-axis. So if you could somehow imagine what is going on in pictures, so you could see that as we look in the direction of x-axis, the function f has a local minima, and if we look at the direction of y-axis, then f has a local maxima. And this is a very complicated situation for us. So this is why I call it a rather concerning example, but this occurs. So here you can see that even though this point, the origin is a critical point where both the partial derivatives vanish. So here f does not have a local maxima or minima. So such a point where the point is a critical point, but if does not have a local maxima or a local minima, such a point is called a saddle point. So we have now introduced you to the notion of maxima, minima, critical points, saddle points, and many other things. In our subsequent videos, we are going to give you a rather concrete method which is called second derivative test, an analog of which you have seen in your one variable calculus, which will be helpful for you to determine whether a function has a maxima or a minima at a given critical point.